you all for joining me here at the end of the day. My name is David McDonald, and I work on the Volcano team at Volatility. And I'm going to share some work with you that I've done on kind of a side project that hopefully y'all can make use of to write better PowerShell detections, save a lot of time when you come across the obfuscated PowerShell, and maybe even make some sweet upgrades to your NeoVim config if you're a NeoVim user. Do we have any of those today? Nice. Cool. All right, so memory-only PowerShell threats. Up here at the top, we've got kind of a classic example of a PowerShell command that is going to run code through the invoke expression commandlet. Shortcut here is IEX, which is very common. This is going to download something over the internet from a server and just execute it directly in memory. And this causes all kinds of problems because, for one, if you use file-based scanners, you're not going to catch this. It uses PowerShell, so you can live off the land and avoid detection based on custom binaries. The evidence is going to disappear whenever you reboot the system or the process is going to exit. If it's obfuscated, it's going to slow down analysis. You're going to be slower to get actionable intel out of the PowerShell code. And it's going to evade telemetry like command line logging, which is a useful data point that people usually use. And when the PowerShell has multiple layers of obfuscation, things can get really difficult. So this is not a new threat, but it's still very prevalent. This is an example from August of last year from the Google Threat Intelligence team, the Peak Light PowerShell downloader. And you can see up here at the top, it implements a custom function that is basically the equivalent of Python's unhexlify. Calls that on a giant string right there, and then decrypts it with AES and is going to execute it down there at the bottom. If you see that ampersand right there, it's going to load the whole thing into a string. I'm guessing that is IEX, since it's a substring of 0 to 3. Followed by a script block. Here's another example from Qualys. This was a PowerShell-based shellcode loader, Remcoast rat. And it uses these regex matches over and over and over again to load binary data into the script and then inject it into memory. So it's going to be kind of a theme, is this like reuse of code snippets to hide what you're doing in the PowerShell scripts. Here's a particularly nasty example from the R77 rootkit, which is an open source rootkit on GitHub. It becomes absolutely unreadable. And the way that they do this is in the install.c file, they load a large random binary blob into memory, and they're going to obfuscate all of the variables and string literables within the program. So here's an example from their source code. Up there at the top, it calls get random bytes, and in a loop down below, you can't see the actual switch statement, but it uses the random bytes to determine what kind of obfuscation to use. So every single time you run this installer, you're going to get a new version of the obfuscated PowerShell, which makes it very hard for you to detect with static signatures, regular expressions, things like that. Here's another example from Emotet PowerShell payload. And this was one of the first ones I looked at when I started messing around with this project. It uses a lot of just like string formatting, string splitting, concatenation, character casting in order to completely hide all of the data within it. Now, if you did have script block logging enabled on your system, you would see this in its mostly deobfuscated form. But number one, you usually don't want to get to the point where it's in your script block logs. And number two, you might not be getting it from that source in general. You might have acquired it in some other way, and you want to analyze it quickly. And here's another example from Iced ID, which just stands out visually as very clearly malicious. They use random comments in there to kind of skew signature detection. And build a byte array out of memory using arithmetic shifts. So for us, it's very easy to see that this is malicious because we have kind of an inherent understanding of syntax trees. But for machines that are trying to detect these things using signatures, it's very difficult. Now, your first line of defense against PowerShell being run in memory is going to be the anti-malware scan interface, or AMSI. And you get one shot, basically, to scan PowerShell scripts before they execute. When you run your code, it loads the AMSI provider into memory, calls AMSI scan buffer, and you get to return an enumeration that basically says, is this clean? Like, we know for sure that it's clean. Is it not clean, detected, or is it not detected, which basically means we don't know, but we're going to let it go by anyway. So there's a lot of AMSI bypasses out there, and I'm not going to talk about those too much in depth, but this one is useful just as an illustration. I split it into two components here so that you can actually see the text. At the top, we have these, this call to add type, and it's going to create a class APIs that loads getProc address, load library, and virtual protect. And when you see those three things, you know nothing good is about to happen generally. And at the lower part of the script, we see an array of bytes being constructed that we're going to use to patch DLL get class object within the mpoav.dll. That's the default AMSI provider that you would find on just the vanilla Windows. At the bottom, you can see that they've obfuscated system.management.automation.amsi utils. Not exactly in a complicated fashion, but apparently enough to bypass it in this case. And on the version of Windows that I was testing, and I did fix it to a certain version so that I wasn't like chasing a moving target when developing this. When you call it, it actually detects this one, which is good. That's what you want to see. And the reason it was able to do that is because it had in its signature database signatures that would match some of these malicious components, like the shell code and the calls at the bottom. So that's good. That's what you like to see. However, you know that, let me go back a slide. So if you see at the top here, I ran this tool called amctrigger.exe, which basically splits your script up into chunks and allows you to scan each of them individually to see what parts exactly are setting off AMSI. So that's how we know for a fact that this in particular is what caused that particular detection. So knowing that, you can just split it up into different components. This is the same upper portion of that script again, except I broke the .NET class out into different components. And then at the bottom, I ran some very basic invoke obfuscation to muddy up the shellcode declarations. And after you do that, that's trying to run the first bypass. It gets detected. Bypass 2 is my updated version. That one runs and returns true. And when I try to run the first bypass again, you can see true, which kind of tells you that AMSI is no longer running on the system. The bypass has been executed. And everything that's going to run in that PowerShell session after that is not going to be scanned. So this is a quote from the actual repo that this bypass came from. It just says system.management.automation.amsi utils is being flagged now. Just do a basic obfuscation of it, like the example below, and it works again. So not exactly a high degree of difficulty or effort required to get past the front line of defense. So some of the first principles of obfuscation are that if there are tools readily available, then attackers are going to use them as long as they continue to work. And these obfuscation tricks in general work because scanners are generally not aware of the programming language syntax. They're just not very well suited for the task, as powerful as they might be in other ways. So you can bypass scanners in EDR, AMSI, Yara, etc. And these obfuscations are also going to waste your analyst time, slow down how quickly you can gather intel, and just make life difficult. I don't think anybody likes to spend time dealing with obfuscated PowerShell scripts. Here's an example of a Yara rule that would try to detect invoke obfuscation in particular. This one is looking for member obfuscations via the call to .invoke. It's looking for string formatting that jumbles up the contents of strings and invokes them dynamically. And the requirements for this are that you hit 11 of the first string, 10 of the second one, and 10 of the third one. But we saw from that earlier sample that you don't need to obfuscate the entire script necessarily. If you're careful with the way that you do it, you can just obfuscate the pieces that are triggering for AMSI, and you can get right by it. Here's another rule for Sigma. This one is looking for these things directly in the command line, which, especially if they use like encoded command, this is going to get right past them as well. So what I wanted to build, and what I ended up building for my first proof of concept, was something that could unwind all of these different levels of obfuscation. And you can see here it steps through the script and glues back all these different pieces, unwinding the different layers of obfuscation until you have something that is actually readable again. And I injected a call to sleep in this one so that you could actually like see it working through, but in reality it's very fast. And the key to this was atomic operations, is what I called them at least. So what you really need to know is very specific pieces of information about the syntax tree. You need to know, for instance, when you're looking at this, that this is a string literal in the text range of 0 to 4. This is an addition operator in the text range of 5 to 6. And this is a string literal at text range 7, 11. And these are all composing an additive expression at text range 0 to 11. So if you had an API that would give that information to you and allow you to access this programmatically, you could do some really cool things. And that's where TreeSitter enters the picture. And funny enough, my initial exposure to this wasn't because I was trying to find ways to deal with PowerShell. It's because I was trying to find ways to make my text editor really sweet. So I saw a YouTube video one day that was like, here's how you get SQL highlighted syntax inside of strings in Python. And I was like, okay, that sounds great because I write a lot of SQL queries inside of strings. So let me see how they do that. And the video went into depth about most of it, but said, if you want to learn how to write the queries, I'm not going to tell you that. You need to go read the manual yourself and figure it out. So I was like, all right, fine, I'll go spend an hour or two reading the TreeSitter documentation. And that's exactly what I got, was the knowledge of how to write these queries and what TreeSitter is generally. And what it is it's a parser generator originally developed for the Atom text editor. It has full integration in NeoVim now. So if you have a TreeSitter grammar installed within NeoVim, you can just run the command inspect tree, and out will pop a window that shows you the syntax tree for your document. The grammars are written in a kind of flavor of JavaScript, and then they're converted to JSON and finally converted into a C parser. So you still have to do the work of writing the grammar, but now it has been done in a way that is programming language agnostic. It only has to be done once, and you wind up with something that is very lightweight. It's written in C, it's fast, it's resilient against errors, and it is fast enough to actually update the tree on every individual keystroke, which is an important characteristic for text editors, but also for writing scanners and deobfuscators, because sometimes you're not going to have like perfect text. So most of the mainstream languages have been implemented very well, and they're actively developed. And there's even a community of people developing grammars for the less common languages. One of the core features of TreeSitter are queries, which allow you to query for structures within the actual syntax tree using what are called S expressions. These are the things that allow you to do fun things like your language injections. Say, please highlight this text as SQL when it's, for instance, a string literal assigned to a variable that ends with query. And you can do a lot of cool things with this once you start really thinking about it. Here's another example in Python. I chose Python because it has a much simpler and easier to read grammar than PowerShell, which is like highly recursive. But what I was looking for here is, hey, I want to find an identifier that is equal to foo. And I wrote the query on the top. That's my query editor. The bottom left is the syntax tree browser within NeoVim. And on the right is my actual document. And if you look at the top there, you see ID. That's not text that I typed. That is the editor pointing out that ID matches this capture that I've defined here, which matches foo. Here's another example, and this one is kind of a good prelude for what I would be doing with PowerShell to deobfuscate the simplest obfuscations like string splitting. So we're looking for a binary operation. On the left side is the string hello. On the right side we're looking for a pattern match for whirl, and then we're going to capture all this within a capture named hello world binary, and we also have two captures for string 1 and string 2. And what the query results are going to expose to us is access to all of those different captures, including the ranges of the document that they exist in. So I started looking for a PowerShell grammar at this point because I had also been exposed to some obfuscated PowerShell. And I noticed that while Microsoft's repo was kind of stale and would no longer work with the current version of TreeSetter, the Airbus cert team had forked it and had brought it back to life in such a way that it could actually be built into a usable grammar. So that was exciting. If a cert team is developing this, then I'm probably on the right track for doing some cool stuff for PowerShell deobfuscation. The first avenue I went down is just what can I detect with TreeSetter for obfuscated PowerShell? And this is a query that kind of both highlights the complexity of the grammar. It's highly recursive, but also shows you how you can target specific things within the PowerShell tree. This is just looking for format strings, which is a very common characteristic of invoke obfuscation. Like this. We're looking for an invocation operator with a format string inside of the parentheses. Now you can imagine that that would be very difficult to write a regular expression defined because you have no guarantees about what order these two placeholders are going to be in. But with TreeSetter, you can query this exact structure. So as a test, I ran invoke obfuscation over an entire repo full of like 600 and something clean PowerShell scripts. And then I ran that YARA rule against it and got 86 hits. Now, this is probably because some of those scripts are just not large enough to trigger the 11, 10, 10 hits required by that YARA rule. But I used a tool called TreeGrepper, which is an open source tool that lets you run queries for run TreeSetter queries for a language against source code documents. So you're searching for programming language syntax features instead of text. And it came up with 616 hits. So it's pretty much perfectly detecting all of these format string commands here. That's the output of the tool, just showing you exactly what you're looking for. Now, there are existing methods for deobfuscating PowerShell, this being one of them, which is not always a bad idea. Sometimes that's just the tool you need to just run it in a sandbox and see what comes out. But that also takes a lot of time to do, and you can't do it for every script that runs in an environment. There's also machine learning-based detections like revoke obfuscation, which is written by the same author as invoke obfuscation. This uses machine learning feature extraction and comparison. And it works well, but it is for detection only. Yeah, so it doesn't deobfuscate the code. It will just help you find the bad stuff. And then there's actual deobfuscators like PSDetect and PowerDecode. These do work for deobfuscation, but they are for deobfuscation only, not necessarily for detection. They run in a PowerShell session themselves, so it's pretty heavyweight. It still requires a sandbox because you can't guarantee that you have exactly gotten rid of every single malicious thing within the script. And it doesn't scale well when you have, hundreds, thousands of scripts running across hundreds or thousands of machines in an environment. And it can't handle corrupt data because if you give the PowerShell interpreter an invalid syntax tree, it's just going to fail to run entirely. Here's an example of how they would patch those malicious functions to deobfuscate. In this case, they're just overriding invoke expression with a right host of commands. So it just prints what it would be running instead of actually running it. And there's a lot of challenges associated with dealing with these obfuscated PowerShell scripts. You can get them from a whole lot of different places, file collections. You can still have obfuscated contents appearing in your 4104 script block logging. You can pull them down from C2 endpoints or open directories. It can come from cached files in memory, in which case we quite often see pages missing or smeared. It also see a lot of, things paged out or smeared in processed kernel or free memory. And maybe even in rare instances, you pull a script out of network traffic or something. So you want something that is going to be scalable. You want it to be able to run in cross-platform environments, and you want it to be able to process massive amounts of data across an enterprise. So some basics of PowerShell obfuscation. Invoke obfuscation is the most famous of these tools. And it has several different methods available to you. The ones that I focused on most for this project were the token and string manipulations. So for token obfuscation, you can see them do things like insert backticks into the command, or dynamically invoke a command from a string by concatenating all the pieces together and using this command invocation operator, or using format strings as well in a similar fashion. And these are trivial to detect with TreeSitter. It's kind of cool that the things that make these techniques so effective and evasive for signature-based scanners are exactly the features that make them pop for a TreeSitter-based scanner like this. So this is a query that would detect backticks in a command name. And again, trying to write a regular expression that is going to detect backticks like this is going to be pretty much impossible. But in this case, we can just write a query that says, hey, find me all command names where the command name matches literally anything with a backtick at the front, middle, or end. And here, again, is running a different query that I cooked up for detecting splat concat with tree grepper and using PowerShell across all of those scripts. Again, very accurate. It shows you exactly what you're looking for within the obfuscated script files. And then you have these string obfuscations, which basically take your entire script, bundle it up into a string, and then dynamically invoke it once again with that command invocation operator. This is another classic technique, is using static environment variables from Windows environments to dynamically construct things like IEX so that you're not referencing those letters directly. But we can actually detect these, once again, pretty easily, very easily, and replace them with their constituent parts if you know what those static environment variables are defined as. Here's a query that detects that exactly. Looking for an element access, which is indexing into the environment variable. Within any variable that matches PS home case insensitively. You also have typecasting, which is hiding string characters through cast operations from integers. Very simple, but still effective against signature-based scanners. So when I built the engine, I developed a set of queries and callback operations that would be performed for each of these little atomic operations, and basically just ran them in a loop until you stop detecting things. And at that point, that's when I had my functional prototype for this. Another useful quality of life enhancement for analysts is the ability to just rename variables, because in almost every single script that I look at, you see these garbage names that just increase the mental load as you try to analyze a script when you are remembering 6 meaningless variable names, you can instead replace them with something like this, which is kind of like a Docker container name, just so that it becomes meaningful and persists in your memory a little bit better. And once you start bundling all these queries together, you can do even more things, like advanced unpacking of something like this. So here we have a script block, which is going to first require you to glue back together all of these string concatenations, format strings, convert that from a base 64 string into a byte array, and then decompress it as a gzip string, and finally create a script block, and once again invoke it with that command invocation operator. So because the queries can be designed in such a way that they won't fire until you only have a single string argument within the call to from base 64 string, you just run that engine, it processes it, and then finally, once you've worked through all the hits in the middle, boom, out comes your deobfuscated script. So as I mentioned before, it's really good at handling errors because as you work in a text editor, your document is not going to always be in a syntactically complete state. You don't want all of the syntax highlighting in your document to just completely break the second you don't have a terminated string literal. So it uses what are called error nodes to just be placeholders when it can't parse something effectively, while everything to the left of it is still parses and forms a valid syntax tree. Here's an example of that when you run it in PowerShell. You'll see that, I think I have to click, do I have to click play? I think it just takes a minute. Yes, okay. So it says the string is missing the terminator. If you were using something like PS decode or power decode, you wouldn't be able to use it on this without going and fixing up the script. But this is that same engine working on a broken PowerShell script because it's still able to understand all the nodes to the left of that invalid string. So about the time I finished that prototype, the Airbus team again released another cool tool, which is called -1, which was really awesome to see because it is very similar, but also completely different. And it's a unique opportunity to see a different black box implementation of something that uses a completely different approach. So this thing is also a PowerShell deobfuscator, but it uses a completely different technique of a tree traversal combined with a visitor pattern. So you define these two traits, rule mute and rule. This is in Rust. And you have a type associated with it. In this case, it's PowerShell. And you get to do something every time you enter or leave a node. So you do a depth first traversal, and you have the opportunity to mutate the tree or just record information about it in general. So it opens up a whole lot of possibilities. If you wanted to do statistical analysis of the tree or hash the tree structure, for example, like agnostic of any actual variable names, string literals, etc. So this is -1 against a Rimcoast rat sample that I pulled off of Malware Bazaar. You can see this is just a giant string being loaded into a variable, unloaded with from base 64 string, and then invoked with PowerShell. So when you run that, you get the original call to PowerShell, but the variable is gone. It has been unpacked from base 64 string into this giant string here. But you can see that there are still some things that are not quite finished. We have a lot of obfuscations remaining in this text. So how can we extend this? Well, if we look at the syntax tree for what you just saw on the last slide, it would look like this. You have a program, statement list, pipeline, command name, that's PowerShell here. And at the very bottom, you have as its argument an expandable string literal. So let's write our own rule and add it into -1. This is going to perform a number of checks on the node. We're going to see if it's a command and if it has 2 children. We're going to see if the command name, when you lowercase it, is PowerShell. And finally, at the bottom, what we're going to do in that case, if it's PowerShell and it has only a single string as its argument, is we're going to initialize an entirely new deobfuscation engine deobfuscate that string, and at the very end, if you see node.set, this is where rule mute comes into play. So you basically replace everything in that node with a newly deobfuscated PowerShell syntax tree. And this is what you come out with on the other end instead, which is similar, but you can see that at the bottom, all of those remaining obfuscations are gone. And what's really cool about these rules is that they kind of like multiply, they're force multipliers with each other. Every single one that you add makes all of the others a little bit better at deobfuscating. So at this point, I was like, okay, we have a really great library for dealing with obfuscation in Rust. And we know that the anti-malware scan interface is sometimes not so great at detecting its own bypasses. What if we built them together into a single tool? So there is Rust for Windows. Note the complete lack of documentation. I was able to finally, thanks to some person on Stack Overflow who outlined exactly what you need to do to register and instantiate COM classes in Rust, I was able to get this working. So you not only have to implement the anti-malware provider interface, but you also have to do all of the Windows boilerplate that is a little unfamiliar to me because I don't write COM classes. So here's our original example again. This is a split view between my PowerShell session at the top, and at the bottom is tailing a very kind of crummy log file format that I wrote just for demonstration purposes. But what this log file is going to show you is some metadata about the file, and then if it was obfuscated, the deobfuscated script blocks at the bottom. So let's run that second bypass from the original slides that did successfully bypass AMSI, but this time with our custom AMSI provider loaded into Windows as well. And you can see that it blocked it because malicious content was detected. As we scroll up through the log at the bottom, you can see that it has completely reconstituted the original obfuscated script. And I have a simple string match here for system.automation.amcutils, which previously had been split into a whole bunch of different components. Again, at the bottom there, that's the text as it appeared deobfuscated from the new AMSI provider. So there's this PowerShell obfuscation Bible that I found on GitHub, which I had a ton of fun with when I was working on this as well, because it puts forth a whole bunch of techniques for obfuscating PowerShell that are kind of a perfect testing ground for this new method of looking for PowerShell threats. For example, attempting low entropy obfuscation. At the top, you have a standard kind of reverse TCP shell, and they have hidden it from malware scanning engines by obfuscating the variable names with a bunch of garbage here at the bottom. Now, the authors raised the point within the GitHub repo that this is going to set off some scanners because you've increased the entropy of the document. And what they propose is instead to do this, which is, you know, pretty obvious to us, again, but it's also obvious to tree sitter, because what we can do is we can write a rule that looks for strings that are of a certain length, but below a certain entropy threshold. So let's take this very simple example and see what we can do with this. This is just, you know, horrible variable names. This is also good for busting bad developers. So when we run this, you know, it blocks this as malicious, so to speak, because it's messing with the program entropy. And we see all these hits on the bottom for variable entropy. Another technique that they proposed is commandlet quote interruption. And as you saw from before, it was very, very easy to write a rule that detects any command names with backticks, quotes, or double quotes in them, because we can target that specific type of node specifically. Another thing they proposed is comment manipulation, adding junk comments here and there to break apart signatures. And you can pretty much just bulk delete these now because comments have their own node type as well. Now, one of the even more powerful features of this -1 framework that I really had a lot of fun playing with is data inferencing. And what this does is it actually infers the data that is being held at a node within the tree. So for example, it can tell you, hey, at this node here, we have a PowerShell array containing these exact values. Or here, we have a string containing, some secret key, for instance. And this unlocks a whole lot of really interesting things. And at this point, I was like, okay, we've got AMC, we've got tree setter. Now let's fold in Yara. So at the very top here, you can see this function, which is actually the exact same function from that peak light sample I showed you earlier. This is that unhex function, but even further obfuscated by doing some invoke obfuscation stuff on that string there. And it's going to be called on a giant format string. And right here you can see the 4D5A, which is characteristic of an MZ header. And that's all going to get stored in a variable here. But what's going to happen is that with data inferencing, it is going to know for certain that inside this variable foo is a giant Python or PowerShell array of bytes. So we can run the simplest rule in the world, which is PE with Yara X, actually with inside our AMC provider as well. Because I think if you have PEs hidden inside of your PowerShell scripts, that's something you'd want to know about. So we run the program on that exact script. You can see that it comes out not only deobfuscated, but we get an exact hit on Yara for is PE at a specific range within the document. So now all the rules that you've worked really hard to develop for things that you would find in memory, your shellcode, your malicious executables, can be leveraged on PowerShell scripts as well. And that's it. It looks like I accidentally deleted my conclusion slide, but happy to take any questions at this point if y'all have them.